let's build another fractal. I want to build the classic dragon curve, which a lot of people don't think of as a curve because it's not got curvy lines. It's made of all straight lines, but mathematicians sort of curve is a line, if you like. This is a classic because it was kind of got into popular culture. You can build it in many ways. So let's just reference where it turns up. First of all, if you've ever read the book Jurassic Park, you may remember the film from the 90s as well. I love the book. I love the film. In the book, Michael Crichton, when he wrote it, at the top of each chapter, he puts an image of the dragon curve, except it's not obvious that it's the dragon curve. In the first iteration, it looks like a line, and then it looks like a kinked line with and then over the course of the chapters, the reveal of each chapter heading is that things are getting more complicated. And this is the theme of the book, is that simple starting points lead to unpredictable results. And that was the kind of the warning that Crichton had in his don't bring dinosaurs back to life. This is a complicated system. It's going to get messy. It's kind of missing the point of chaos theory, but in the book and the film, there's a mathematician called Ian Malcolm, who is this chaotician, I think they call him. He's a mathematician who doesn't really understand chaos theory, but is trying to make a nice point that, in particular, biological systems get complicated quickly. And that's not really the point of chaos, but chaos is hard to define in many different ways, and it's a relatively newfangled thing. It's only been around since the 70s and 80s, really, 1970s, 1980s, so it's a recent piece of mathematics. Let me show you, I'm not going to talk about chaos theory in general here, let me show you the dragon curve and one way to build it. So here is a piece of paper. It's just got a strip of paper, nothing particularly special, but that's our first iteration. It's a line. If I fold it in half, and actually I need to remember which way I'm doing it, so I'm going to fold right to left. If I fold it in half, I will get a line half the length, but I'm going to open it up and make so that every part of the shape is at 90 degrees, and here we have an L shape. If I fold it again, that was the first iteration, if the line is 0 iteration. If I fold it again right to left, we get a quarter length line, but this time if I open it up so everything's at 90 degrees, we get a different shape. And what shape will it be? It'll be that shape. No idea if this is going to focus on that nicely, but if I bring this back into focus, okay, there. It's still not really obvious what's going on, so I keep going right to left, fold it again, and this time open it up to 90 degrees again. It's quite interesting to try and predict what you think will happen if you've never seen it before, and even if you have, like, so there was our first one, but if I fold it out again here, we get that shape. And these are approximately 90 degrees, you can see, I hope, because it's got some thickness to it. Okay, let's do one more time. Again, fold in the same direction every time, right to left, this one. And you can see why I started with a long piece of paper, because this is going to get impossible to actually do, partly because folding is difficult, and partly because things are getting small. The individual segments are sort of half as long each time. So let's unfold this all the way, and then do that rule about 90 degrees. Now this is going to get hard to arrange, but you already see, I think, that we've got a sort of closed loop here. Now not every fold is quite 90 degrees, but here is the shape that we get this time, and I can turn it, and you can see that just in where this finger is here, is closed a loop. Now it's already slightly intriguing, and it's nice that you can sort of physically do it with a piece of paper. You don't need any special kit. But what is this shape that is emerging? Because the shape that it tends towards is called the dragon curve, and the iterations towards it are part of the game. So we're going to build this in GeoGebra, and we're going to build it in two ways, which do sort of fundamentally, it's common in fractals that you can describe them in two ways, but do sort of capture the two definitions of the dragon curve, one of which is to do with the fact that it's kind of an unfold of the previous one. If you take that thing and unfold it again, then you get this shape eventually. And the other one is to do with taking a line and then making it into a kinked line. And they're kind of different ways of saying the same thing. So let's build both now. Okay, I've got a blank GeoGebra window, and this curve is going to start with a single line. I'm going to do the first version is where I'm going to start with 2 points and put a line segment between them, and then turn that line segment into a kinked line segment. So this is going to be the sort of version where we build up from a line to 2 lines instead of the unfoldy version. We'll try and do that next. As ever with the iteration command, which I'm going to use, if you haven't seen me use that or you want to know more about it, check the previous videos when I talk about how to use the iteration command to build fractally shapes. I'm going to just go straight in here and put a segment between the two, and this segment is what I want to iterate on. I don't want it to have to know about A and B in this case. What I'd like to do is basically pass the command a line segment and then spit out a list of line segments, which is the 2 new line segments. So I'm going to have to deal with the list protocols and figure out how to start with a list, even though it's not a list to start with, and all that thing. I think it'll be fine. So let's do a few sort of practice steps. The next step of the iteration is just to get a line segment up there and there. And so they're the original line segments. They're not going to be half as long in this case. It's kind of like the sides of a square, of which that's the diagonal. So it's actually going to be 1/√2 scale factor. If you don't believe me, go and draw some Pythagorean triangles. Let's figure out a way of doing that. So like always with an iteration command, I need to make sure I'm referencing the thing I'm starting with, which is just the line segment. I can't mention A and B, even though they are there. I just want to be able to pass out a line segment called F in this case, and use that to figure out how to make the next step. So for example, I can rotate the line segment F by 90 degrees, pi by 2, but not about the origin, which it will do if I don't tell it where to go around. So let's go around. I could say A, but I don't want to reference A, so I'm going to use the fact that there's the point command to get a point on F with parameter 0. So that'll be the beginning of the line segment. And that has rotated 90 degrees. It turns out I didn't want it 90 degrees. I wanted it 45 degrees. So you live and learn. And here's the first irritation we've got with this command, is that although I typed it in using point F0, it's turned it into a segment with A dashed and B dashed. And it's made A dashed and B dashed over here as sort of auxiliary points. And there's where the command was, to get A to A dashed and then B to B dashed. So that's a bit frustrating, but the original command I typed is still there in the history. So I'm just going to copy that and delete all the things that I made I didn't want, and try again. This time it's pi by 4 I think I want, I'm pretty sure. There we go. It's also too long. So let's also enlarge that, or rather shrink it, but enlarge it by scale factor 1/√2. And center the enlargement at the same point, so point F0. Right, so that's made one of the new line segments. And let's make another one. That command, copy that. Let's do it again. But this time, do it about the other point, the other end of the line. And I want it to go the other way round. So I don't want to go pi by 4, and I'll go negative pi by 4. And I think that's done what I want. So that's iteration 0, the flat line, to the kinks line, iteration 1. There are some problems which we'll see trying to get to the next level. So I think it's always good to try and get a couple of practice iterations before you go for the full command. And the other problem is this is not a list yet. I'd like to be able to pass in a line segment and get a list of line segments out. So let's just make these 2 previous commands, which were that one. I'll put a curly brace at the front to make this a list, and that's the one I just did. Let's change that to 1s again and put the -1 in again. Close the list, and now I've got a list of line segments. I can delete these 2, they're kind of irrelevant. So I've got a line segment F, and it's turned into a list of line segments. And if you check the command, it has done annoying things. You can see it's mentioning A and B, and that's going to cause a problem. But the command I actually typed in is still there in the history, so I'm going to copy that before it disappears into the ether. And that one doesn't mention A's and B's, it just mentions F, the line segment. Okay, that's copied. The practice run I really need to do is be able to take the next list, that L1 it's called itself, and get the next version. So I want to do the same command on L1. And so I need to zip through the command I've just got. I need to zip through the list L1, do that command on the bits of list L1. So let's do a zip, and I'm going to paste in the command I just used. Now, slight irritation, F already exists, but in a zip command, it needs a dummy variable. And actually, I think it is going to override. This is dangerous, but I'm going to leave F in there as long as it then checks in the zip command what F to use and take F from a list L1 in this case. I don't think it's going to use the original F. That is weird, but I can see it is doing something, so I know that's kind of working. It's not doing what I want. Let's press return first and get that locked in before I talk about why it's not quite right. So what it's done is it's taken the line segment and gone to the kinked one. That's what I did already. And this one's taking those 2 line segments and kinking them out, and that's fine. And this actually will make its own fractal, but it's not the dragon curve fractal. Because what the dragon curve fractal does, if you remember from my bit of paper, the first iteration was the kinked line segment, but then it's really hard to see when it's all bent. Like the second one looks like this. It's not a rectangle. It's got that sort of saucepan shape. So I have to focus on over here. Saucepan-y shape here. And that's because the direction the kink goes alternates because of the way the folding is happening. So I need to somehow build into the zip command a way of changing the orientation of the kink each time. And that's okay because I know how to build an alternating sequence with powers of -1. And it's just a question of the rotations. So a zip command can take more than one item. So I tell you what, let's go back to our practice run here. No, this one we got up here. That was our make a new list, but this time it's not zipping anything. No, we better do the zip command. And this one, by the way, can you see it's still just referencing F? I'm just checking on that. That's the second level I've tried it. So the zip is running the Fs from L1, but I'm going to also put another variable into the zip command. Let's call it K for some multiplier. And K I'd like to come from a list of positive and -1s. Sequence -1 to the power of some other dummy variable. Let's use P. I don't think P's been used. And P runs from 1 to how long it is. It's the length of L1. So let's do length L1. Lots of brackets to close. I think that's all of them. That hasn't changed anything. All right, so the zip command now has a K variable floating around, but it's not doing anything with that K variable. So I'm going to put the K in front here. I think that's going to make the first one negative. So maybe I want to put -K. And this one I'm just going to put K times that. And we should see a change in the shape. And we do. Now it's hard to see what's going on. Let's just check. Hide the original. That is the shape I was after. It's upside down from when I was holding it. So I now know I've got the alternating thing going on, and I've got the command. The only other problem is, though, this is a list of lists, and I need to be able to iterate over a list, not a list of lists, so I'm going to flatten this list. And now I've got a list and a new list, which has got 4 items in it, which are all over root 2 times bigger, so root 2 times smaller, whatever that means. And they're alternating. So I think it's going to work, and this is why doing the practice builds is necessary. We're going to go for the full command now. I'm going to grab this command, which is messy, copy. I'm going to type iteration, put the function I just copied in there. It's all there. The catch is L1 is not what I want to iterate over. I'm going to call it Fs for like plural of F. Again, I'm going to gamble on F not being recognized. I think that's dangerous. So this is the length of Fs, and I want Fs to start. I didn't show the protocol here, but you need to give a start value and then a number of iterations. So let's do start value. The list to start with is the segment F. This is the first time the real F gets used. Man, this is terrible, but I think it's going to work. The catch is this command needs a list of starting values, just in case there are more than one. So we need a list of list F, and that's horrendous, but it works, and we'll just do it twice for now. Right, it's done the same thing, which is promising. I'm going to make a slider, which is an integer. I don't want it to get too high, but it's only a one-dimensional line, so it shouldn't matter too much. Let's change this to run to n. Always nervous at this stage. Nice. It's kind of doing what I want, so let's hide my practice run. You can tell by the grin that I'm just relieved this works every time. We don't need the axes or the grid here. I do want this to go back to 0. The 0 iteration should still function. It's always nice that that sort of, and that should be where we started when it does nothing. There we go. Right. First iteration, second iteration, third, fourth. Nice. Maybe you can see why it's called the dragon curve now. I'm not sure it looks particularly dragony, but it is kind of, maybe it's got an Eastern artistic vibe to it, and maybe Japanese art, which used a lot of dragons, is possibly why it gets called the dragon curve. So this is functioning. It was one command. albeit a long command, one slider controlling the iteration. And the nice thing about this version of it is that it's building a list into two lists, or a segment into two segments. So the segments are getting smaller, so the whole pattern doesn't sort of take more space, it just builds in place. And I can still move A and B around to scale it. So I reckon we could get the iteration up higher. It doesn't seem to be chugging too much. Let's go a bit higher. See, I don't want to crash the thing. And you need to be careful with doing iterations that GeoGebra doesn't like, because it's growing exponentially. But you can see that this is tending towards this shape, and actually you get a sense that there is a shape, and actually it's an area. If you're interested in fractal dimension, which I'm going to talk about in another video soon, this has dimension 2. It is a two-dimensional object, despite it being a line. It is a space-filling curve, as they call it. And the space it fills, though, is this amazing fractal shape, which does tessellate, by the way. More on that later on. Let's build this in another way to get another insight into how the structure works. So the other way I want to think about it is much more closely linked to this folding idea, although the catch with this folding and then unfolding thing is that everything's getting smaller. Actually, if you just take a segment and get a copy of it and fold it up like this, then you start to do it. And if you take a copy of those two segments and fold them up, you could create the same fractal, but it will get bigger and bigger, unlike my piece of paper, which is not getting any longer. But that's what we're going to try and do this time. So I'm going to just park this over here and leave that slider alone. Maybe it's risky doing it in the same file, but we'll give it a try. Maybe I'll save it just to make sure. Okay, this time I'm going to start with 2 points again. And I suspect this time it's going to be easier to deal with the points rather than the lines. I'm not sure about that. But if I can get a succession of points which are in the right order, then it's very easy to join a bunch of points together in order with a line. It's called the polyline command. So if I can get the points to iterate in the right way, I can just tag a polyline on the end and we'll get the shape. And that will hopefully remove all the sort of faffing around with the endpoints of the lines business. So maybe I'll work with points this time. I'm reflecting now, why didn't I try and do that with the other one? And there would be a way to do it, I'm sure, with points in the other one. However, let's try it this way. So there's a segment between them, but to get the next fractal, I just want to rotate one of these points. Let's rotate point C about point D. And this time I do want to go 90 degrees, and that's possibly why I was getting confused earlier. Rotate object C by 90 degrees, or pi by 2, around point D. Now, I'm referencing C and D, but if C and D, or maybe a list of C and D, is going to be my starting point, that's okay, as long as they're always going to work. So that's like the next version of the iteration, but that's just made a new point. And I think each time I want a list of all the points in order that define the fractal. So let's start with a list CD. It's called itself L3. Let's rename that to be SL for start list. Terrible name, but never mind. And the new list needs to be the points C, D, C dashed, I think. So let's just do that. The next version is going to be the original list, which is SL. I'm making a list of lists here, but I'm going to flatten it in a minute anyway, so I think that's okay. So I want to take the original list and then add another point, but it could be more points. So I'm going to take the entire original list, which is SL, and rotate it by 90 degrees around the last point in the list. The last point in the list. You can sometimes use function notation, but I think that sometimes goes wrong, so I'm just going to avoid it. Play with it if you want to. You can always use the element command, which takes a list, SL, and the last one is the one at the length of SL. Slightly clumsy, but that will do it. Is that everything? Rotate the whole list by the last element 90 degrees. Okay, it's made a list of lists. So let's flatten it and just check what it's doing. I'm going to hide my originals. Right, so there's the thing I just made. And it does look like it's made the list. The catch is I'm not sure if there are. So first of all, there's a duplicated point in there, and that's not a surprise. It's taken CD and rotated it about D. So D ends up being the same there. But the new list, I don't really mind if there's a duplicated point, because we might need to revisit the same point at a different point in the list because of those closed loops you saw earlier. I don't want to get rid of that. But it needs to be C, D, D, and then the new one, which means I think that second part of the list needs to be backwards. And that, I guess, makes sense. So whatever, you take the whole list and you sort of spin it out, but this time it's starting from the old endpoint. So we just need to reverse that. And there is a reverse command for a list. It's in there. And now you can see it goes that point twice, and then the next point. And I think that is doing what I want. It's also flattening it. I need to do another iteration practice, because now I'm confusing because I've started with a list, but I need to be able to accept a list and run through the list of points. And that is doing it. So it's taking a list, SL, and everything's just referring to SL. So maybe that is all I want. Copy that. Should we go for the iteration? Let's make a new slider. I'm going to call it N2, and we'll go up to 10 to start with. Doesn't really matter. Okay, iteration. I don't want an iteration list. I just want to see all the points. So here it is. Paste in my thing. Dangerously again, I'm going to just use SL, even though it already exists. Hope that the iteration command recognizes it's a dummy variable. There's no zip in this one. That's interesting. I was kind of expecting a zip, but that's okay. So it's going to take the list. Oh, no, careful. I'm going to use, all right, I do need a dummy variable in here. S is just going to be the list of points. That's a terrible word for it, but then S needs to iterate starting with the list SL. N2. I'm worried. Oh, it's doing something, and that's a whole lot better than doing nothing. So press return and let's figure it out. Is that the third iteration? It's amazing how hard it is to see the structure, but by the way, this one was our old one, so let's just get that out of the way over there. This does depend on C and D. You can see this is going to get big really quickly, because every time it's sort of doubling in size, or in length at least. And it's also not a line, so let's make the polyline that I said I would do. Polyline, there it is, list of points, and it's called itself L3. That looks promising. And this time I haven't had to deal with any alternating thing, just because it's unfolding. I guess the alternating bit is coming from the reverse of the list. So it takes a list, spins it around the end of it, makes sure it's in the right order to do the next one, to take that thing and spin it around the end of it. It would be really nice to show that sort of unfolding spin, which we can do quite easily, I think. But let's zoom out and see how this pans out. So this is kind of in the way. Let's just hide that over there. Let's start over here, really small, and see how this goes. Maybe I'll hide all the dots. I just want to see the line. M2 is my practice run. Let's hide C and D, although I might need to move them around later on. Let's go. You get a sense of the spirally nature of this, and it is working really nicely. But it's obviously twice as big each time, unlike the other one, which sort of remained in place. And this is capturing the sort of unfolding nature. So I think that is a success, and we can change the original things to zoom in and out. But they do have to be quite close together if you go high iteration to see the whole thing. Let's see if we can capture the unfolding as a final step to building this dragon fractal, dragon curve. Okay, and this one's still working over there. Look at that, nice. The unfolding, though, each iteration just unfolds to give the next one. So actually, if we just do the same iteration one other step, we've got the next version. And I just want to rotate it. So I could rotate a copy of this around its last point. Let's get a slider up for the rotation. Go with the angle. It's going to work in degrees, but that's all right. It's called itself alpha. And let's just take the last thing. So the polyline G is the thing we want to use. So rotate G by alpha. I need to tell it where to rotate around. So it's the last element of L3. I'm going to use the function notation for a list just to access the... I wonder if that will work. I think that is working. Good. We're rotating that thing. And you can see it. So when it gets to 90 degrees exactly, that is the next level of the fractal. Whee! It's really nice to see it animate. I do need to lock it to 90 degrees, so let's just limit this one to 90. That degree symbol in there is important, by the way. Don't delete it. And now you can see, whoop, and then unfold that again to get the next one. So what we can do is add a little animation, but already this is quite nice. Maybe what I'll do, I'm not going to do a full animation thing, I just want to build a fractal, but I will do one thing, which is when you update the N2, I'm going to go into a bit of scripting here. The slider N2, which is the iteration number for this one, I'm just going to, when it updates, set the value of alpha, which is my rotator, to 0. And what that will do is every time we get a new iteration, we'll see that it will just jump to 0, and so it'll be unfolded, not folded out. That's not the same as unfolded out. Flipping heck, that word's confusing me. Let's just see what I mean. If I drag this around, you can see the alpha's gone to 0, so that's just stepping it up. But if I drag each one up, then it's done the next one, and we can drag up again, and it's there. Drag it up. Oop. Now there's a slicker way to do this, I'm sure. More scripting would be available, but that's enough for now, I think. When you drag this around, you see the fractal build, and if you want to see them unfold, you just see that. Beep. Beep. If I want to do this animate, what I'd do is I'd set a timer slider called T or something, and every time it got to 1, from 0 to 1, I'd reset alpha and then increment N, and just cycle that. But this is already nice, I think, to see how the thing works. And both of these ways of constructing it give me an insight into the dragon curve. Let's just, to finish with, crank it up. So I've let this go to 10. This one going to 10 looks similar, but it's taking less space. And you can see that they do look kind of comparable when you put them like that. I think they are actually comparable. That's kind of a relief. In fact, if I put one on top of the other, yeah, I think they're the same. Now I'm confused myself. Where's C and D? Right, let's get A out of the way over here. But because the A and B one is staying in place, it just gets denser and denser, whereas the other one is just taking up more and more space. So let this one get up to 15 maybe. We're going to have to be careful about the space on the screen here. Keep C and D quite small to start with. And then go up and up and up and up. And actually, you can see that the tessellation is kind of a product of the fact that this is just a spun round version of the original. They're both at 13 now, and you can see how these compare. I could pop out the algebra window and get that out of the way, and we've got a bit more space. So at this point, you play with the aesthetics, and I'll leave you with some nice aesthetic versions of these that I made earlier. That's how to build a dragon curve in 2 different ways in GeoGebra. At least that's how I did it. I'm sure there are many other ways. Hope you're enjoying these things more soon. See you then.